The world feels solid. You knock on a wooden table. It feels hard. You drop a glass. It shatters on the floor. These are facts. They are reliable. The sun comes up. Gravity keeps us grounded. We learn these rules from the moment we are born. This is reality, we think. It's a collection of solid things, governed by predictable laws. It's a machine, maybe a very complex one, but a machine nonetheless. You can take it apart, see how the gears turn, and put it back together. But what if that's just a surface level story? What if the solid, predictable world you experience is just an illusion, a kind of high level summary of something much stranger happening underneath? What if reality, at its most fundamental level, isn't made of tiny, solid bits at all? What if it's made of pure potential, a shimmering, uncertain wave of possibilities? This isn't a New Age fantasy, it's the central, deeply weird puzzle that physics stumbled upon about 100 years ago. And it's a puzzle we still haven't solved. The idea is that before you look at something, before you measure it, it doesn't have a definite state. A tiny particle, like an electron, isn't spinning one way or the other. It's not in one specific place. It's in a state of all possibilities at once. It exists as a wave of probability. And this wave describes the chances of it being here, or there, or spinning this way, or that way. Only when something interacts with it, when it's observed, does this wave of potential collapse into one single solid reality. The one we experience. This sounds crazy. It goes against every instinct we have. But the evidence for it is overwhelming. The math works perfectly. It's the foundation of all modern technology, from your phone to medical scanners. And yet the implication is staggering. It suggests that reality is not a fixed, objective thing sitting out there waiting to be discovered. It suggests that reality is something more fluid, more participatory. It suggests that the universe, on some level, waits for an observer to make up its mind. So let's explore this idea. Let's look at where it came from, what it means, and why it's so hard to accept. We're not going to use complicated math, we're just going to use simple ideas and thought experiments to try and understand this profound shift in how we see the world. Is reality just a wave of probabilities? The answer seems to be a hesitant, mind-bending yes. And that changes everything. For most of human history, we lived in a clockwork universe. This was the world of Isaac Newton. It was a world of certainty. Everything was made of tiny, solid balls called atoms. These atoms followed strict rules. If you knew the position and momentum of every atom in the universe, you could, in theory, predict the entire future with perfect accuracy. And you could perfectly reconstruct the past. Everything was cause and effect. A billiard ball hits another, and it moved. There's no mystery. This was a comforting idea. It made the universe understandable. It was a grand cosmic machine, and we were just cogs within it. There was no room for ambiguity. A thing was either here or it was there. It couldn't be both. It couldn't be a maybe. This deterministic view dominated science for centuries. It worked beautifully for describing planets, falling apples, and cannonballs. It built bridges and skyscrapers. It felt like the final answer. Reality was solid, predictable, and external. It existed independently of us. Our minds were just spectators, watching the cosmic movie play out exactly as it was scripted from the beginning of time. There was no room for free will in this universe. Your thoughts, your decisions, were just the result of atoms bouncing around in your brain, following the same unbreakable laws that govern the planets. You felt like you chose to have coffee this morning, but that feeling was an illusion. The chain of cause and effect leading to that choice was set in motion at the Big Bang. You couldn't have done anything different. It was a neat, tidy, and somewhat bleak picture. But it was logical. And then, at the turn of the 20th century, scientists started poking at the very small. They started investigating the world of atoms and the particles that make them up. And the clockwork universe began to fall apart. The simple, solid billiard balls of Newton's world started behaving in ways that were not just strange, but logically impossible, according to the old rules. They weren't behaving like little balls at all. They were behaving like ghosts. They were behaving like waves. The experiment that truly broke everyone's brain was the double-slit experiment. It's so simple in its setup, yet so profound in its implications. Imagine you have a screen. In front of it, you place a barrier with two thin vertical slits in it, and then you shoot something at the barrier. Let's start with something solid, like tiny marbles. You shoot them at the barrier. Some hit the wall and bounce off. Some go through the left slit, some go through the right slit. What do you see on the screen behind the barrier? You see two clumps of marbles, one lined up behind the left slit, and one lined up behind the right slit. This is common sense. This is how solid objects behave. Now, let's try it with waves. Imagine sending water waves towards the barrier. As the waves pass through the two slits, they spread out on the other side, like ripples from two stones thrown in a pond. These two new sets of ripples interfere with each other. Where the crest of one wave meets the crest of another, they create a bigger wave. Where the crest of one meets the trough of another, they cancel each other out. What you get on the back screen is a pattern of many stripes, not just two. It's an interference pattern with bright spots where the waves added up and dark spots where they canceled out. This is how waves behave. So far, so good. Particles act like particles. Waves act like waves. Now for the weird part. Let's shoot electrons, the tiny particles that orbit atoms. We think of them as tiny marbles, so we should get the two-clump pattern, right? But that's not what happens. When you shoot electrons one by one at the two slits, they land on the screen as individual dots, just like marbles. But after you've shot thousands of them, the pattern of dots that builds up is not two clumps. It's the interference pattern, the pattern of waves. This is deeply strange. Each electron is a single particle. It should go through one slit or the other. How can a single electron traveling by itself create a pattern that requires it to interfere with something? The only thing it could interfere with is itself. It's as if the single electron goes through both slits at the same time, as a wave interferes with itself and then lands on the screen as a single particle. This is where the idea of a wave of probability comes from. The electron leaves the gun not as a tiny ball, but as a wave of potential. This wave spreads out and goes through both slits. The wave then tells us the probability of where the electron might be found. The bright stripes in the interference pattern are the places where there's a high probability of finding the electron. The dark stripes are where there's a low probability. The electron doesn't exist at any single point until it hits the screen. Before that, it's just a cloud of possibilities. But it gets even weirder. The scientists who first saw this were baffled. They thought, okay, we need to know which slit the electron is actually going through. This both slits at once thing is nonsense. So they set up a detector, a tiny little camera or sensor right by the slits, to watch and see which one each electron passed through. And the moment they did that, the moment they observed the electrons, the interference pattern vanished. The electrons started behaving like marbles again. You got two simple clumps on the screen, one behind each slit. The act of looking, of measuring, of simply gaining the information, which slit did it go through, forced the electron to choose a path. It forced the wave of probability to collapse into a single, solid reality. The ghost in the machine disappeared the moment you shined a light on it. This is the core mystery of quantum mechanics, the observer effect. The very act of measurement seems to change the outcome. An unobserved particle is a wave of possibilities. An observed particle is a single, solid thing. It's as if reality holds its breath until it's being watched. This led to the concept of the wave function. The wave function is the mathematical description of that wave of probabilities. For any given particle, its wave function contains all the information about its possible states. It describes the likelihood of the particle being in this location, or that one, of spinning up or spinning down. But it doesn't give a definite answer. It's a recipe of pure potential. Think of it like a weather forecast. The forecast might say there's a 70% chance of rain, a 20% chance of cloud, and a 10% chance of sun. The wave function is like that forecast. It describes all the possibilities and their likelihoods. The act of measurement is like opening your window and looking outside. When you look, you don't see a 70% chance of rain. You see one thing. It's either raining or it's not. The cloud of possibilities has collapsed into a single fact. The problem, the one that physicists still argue about today, is why and how this collapse happens. What is so special about measurement? What counts as an observer? Does it have to be a conscious human being? A camera? A Geiger counter? A dust mote bumping into the electron? This is called the measurement problem, and it has led to several competing ideas about the nature of reality. The first and oldest is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg. It's the most straightforward and, in some ways, the most unsatisfying. It simply says that the wave function collapses upon measurement. That's it. Don't ask why. It just does. It posits a universe that is fundamentally divided into two realms, the strange quantum world of probabilities and the normal classical world of definite outcomes where we live. The act of measurement is the bridge between them. In this view, it's meaningless to ask what the electron was doing before you measured it. The question itself is invalid. The only reality is the measured reality. Before that, there was only potential. But this feels like a cheat. It doesn't explain the mechanism of collapse, and it raises all sorts of questions about the observer. If a Geiger counter can collapse a wave function, does that mean the Geiger counter exists in a state of probability until a person reads its display? Where does the chain stop? It seems to push the problem up the line until it reaches a conscious mind. This led some physicists, like Eugene Wigner, to propose that consciousness itself is what causes the collapse. That the universe needs a conscious observer to become definite. This is a very provocative idea, placing humanity at the center of the creation of reality. It's also an idea that makes most physicists uncomfortable, as it mixes objective science with subjective experience. Because of this dissatisfaction, other interpretations emerged. One of the most popular today is the many worlds interpretation. Proposed by Hugh Everett III, this idea does away with the collapse of the wave function entirely. It says the wave never collapses. Instead, every single possibility encoded in the wave function becomes real. It just happens in a separate parallel universe. When you measure the electron at the two slits, the universe splits. In one universe, you measure the electron going through the left slit. In another, identical universe, a copy of you measures it going through the right slit. Both outcomes happen, both are equally real. Every quantum measurement, every probabilistic event is a branching point for reality. This means there is an unimaginably vast, perhaps infinite, number of parallel universes branching off from each other every fraction of a second. There's a version of you that chose a different breakfast this morning. There's a version that took that other job. There's a version where the dinosaurs were never wiped out. Everything that can happen does happen somewhere in this grand multiverse. It's an elegant solution because it gets rid of the special status of measurement and the mysterious collapse. The equations of quantum mechanics just work, always, without any sudden breaks. But the price is an astronomical number of unseen worlds. It's a trade-off between a weird process collapse in one universe and a simple process that creates an infinite number of them. There are other ideas too. Pilot wave theory, for example, suggests that the particles were always solid little balls with definite positions. We just didn't know what they were. They are guided by a pilot wave that we can't see, and this wave is what creates the interference patterns. This view brings back Newton's determinism, but it introduces hidden variables that we can never directly access. It's a minority view, but it shows that there is no consensus. The greatest minds in physics can look at the same evidence and come to wildly different conclusions about the fundamental nature of reality. So, if the world at its smallest level is just a shimmering wave of probabilities, why does the world we live in feel so solid and predictable? Why isn't my chair a fuzzy cloud of potential locations? Why doesn't my car sometimes decide to be on the other side of the garage? The answer seems to be a process called quantum decoherence. The key thing about maintaining a wave of probabilities is isolation. The electron in the double-slit experiment can act like a wave because it's mostly on its own. It's in a coherent state. But a large object, like a chair, is not isolated. It's constantly interacting with everything around it. Air molecules are bouncing off it. Photons of light are hitting it and reflecting into your eye. The floor is pushing up on it. Each of these tiny interactions is a form of measurement. Each air molecule that bumps into the chair observes its position. Each photon that reflects off it carries away information about where it is. With trillions upon trillions of these interactions happening every nanosecond, the chair's wave function is being collapsed constantly, instantly, and overwhelmingly. All the weird quantum possibilities, the chair being slightly to the left, or upside down, or in the next room, get canceled out almost instantaneously. The only possibilities that survive this constant environmental measurement are the ones that are consistent and stable. The chair being a solid object in one definite location. So the solid, classical world we see isn't a different world from the quantum one. It is the quantum world just viewed at a massive, messy, and constantly interacting scale. Decoherence explains how the familiar, predictable reality of our everyday lives emerges from the bizarre, probabilistic reality of the quantum realm. The weirdness is still there, under the surface, but it gets averaged out on a large scale. Your chair is a wave of probabilities, but the probabilities are so overwhelmingly spiked at one particular location and state that it might as well be a solid object. The maybe is still there, but it's a 99.999% yes and a 0.000.1% no. This has profound implications for one of the oldest philosophical debates, free will versus determinism. The old clockwork universe of Newton was purely deterministic. If you could know the state of everything, you could predict the future. Your choices were an illusion, but the quantum universe is not deterministic. It is probabilistic. At a fundamental level, the universe seems to have an element of pure randomness to it. When a radioactive atom will decay is not predetermined, it's a matter of probability. We can say that in a large sample, 50% will decay in a certain time, but we can never say when one specific atom will do so. This seems to break the chain of cause and effect. It introduces a genuine element of chance into the fabric of reality. Does this open the door for free will? Some people think so. They argue that if the future is not set in stone, if it's just a set of probabilities, then perhaps our consciousness can influence which of those probabilities become real. Maybe our minds can nudge the quantum events in our brains, turning a maybe into a yes, and allowing us to make a genuine choice that was not predetermined. It provides a potential space for something other than just cause and effect to operate. But others argue that this doesn't help at all. Replacing strict determinism with pure randomness doesn't give you free will. It just gives you randomness. If your decisions are based on the random decay of an atom in your brain, you aren't choosing any more than you were in a clockwork universe. Your actions would be unpredictable, but they wouldn't be willed. They would be arbitrary. A random choice is not a free choice. So quantum mechanics might kill old school determinism, but it doesn't automatically give us free will. It might just replace a predictable machine with an unpredictable one. The question remains open. We don't understand consciousness well enough, and we don't understand quantum measurement well enough to know if or how they might be connected. But the conversation has shifted. The universe is no longer a simple machine. It's a game of chance. And whether we are players or just spectators is one of the biggest questions left to answer. This leads us to the most speculative and mind-bending aspect of this whole story, the role of the mind itself. The idea that a conscious observer is needed to collapse the wave function is, as mentioned, a fringe view in physics. But it's an idea that won't go away, because the problem of the observer is so central. Let's think about what this would mean if it were true. It would mean that the physical world, in some sense, depends on a mind to bring it into focus. Before a conscious being observes a system, it exists in a ghostly superposition of all possible states. A tree falling in a forest with no one or nothing to hear, it would not make a sound. In fact, the tree itself would be in a state of fallen and not fallen simultaneously. The universe would be a sea of unrealized potential until a mind looks at it, and by looking, forces it to become one definite thing. In this view, we are not passive observers of a pre-existing reality. We are active participants in its creation. Our consciousness is the catalyst that transforms the fuzzy quantum maybe into the solid classical is. The universe and the mind are not separate. They are locked in a co-creating dance. And reality is not just what is out there. It's a relationship between out there and the in here of our awareness. This sounds more like philosophy or mysticism than science, and it's true that there is no experiment we can perform to prove it. How could you test what reality is, like when no one is looking? The moment you look, you change it. It's a perfect logical loop, but it's an idea that resonates with some of our deepest intuitions. Our subjective experience feels primary. We experience the world through our consciousness. What if that experience is not just a passive reception of data, but a fundamental act of creation? This doesn't mean you can wish for $1 million and make it appear. The laws of probability are still in effect. The wave function of the atoms in the air is not going to suddenly have a high probability of rearranging themselves into cache. The probabilities are set by the laws of physics, but it might mean that at every tiny, uncertain juncture, consciousness plays a role in steering the ship, in selecting one path out of the many that are available. It changes our place in the cosmos. We are no longer insignificant specks of dust in a vast, indifferent universe. We are the universe's way of observing itself, of becoming real. We are the bridge between potential and actual. This is a powerful and perhaps egotistical idea, but in a quantum world where the act of observation is so inexplicably important, it's an idea that is hard to dismiss entirely. So, what does it all mean for us living our daily lives? Does knowing that your table is a collapsed wave of probabilities help you pay your bills? Probably not. On a practical level, the classical solid world is the one we have to deal with. The laws of Newton still work just fine for driving a car or baking a cake, but understanding this deeper reality can fundamentally change how we see the world and our place in it. It injects a sense of wonder and mystery back into a world that can sometimes feel mundane and overly explained. That solid table is not just a boring lump of wood, it is a torrent of quantum activity, a collection of trillions of possibilities that have been focused into a single momentary reality by the act of observation. It is a settled storm. It also changes how we might view the future. The future is not a destination we are traveling to on a fixed track. It is a cloud of probabilities, a wave of potential, and Our choices, our actions, our very attention might be what helps collapse that wave into the future we experience. This can feel empowering. It suggests that reality is more fluid, more malleable than we thought. It's not set in stone. It is constantly being created, moment by moment. It can also be unsettling. It dissolves the hard line between ourselves and the world. The objective reality out there becomes tangled with our subjective experience in here. The world is less solid, less certain. Our universe is built on a foundation of Mabe. We are living on top of a deep, strange, and probabilistic ocean. Ultimately, we are left with a profound mystery. Science, in its quest to understand reality, has revealed a world far stranger than any of our ancestors could have imagined. We started by looking for the smallest, most solid building blocks of the universe. Instead, we found ghosts. We found waves of pure potential. We found that the act of looking changes what we see. Is reality just a wave of probabilities? At its most fundamental level, it seems to be. But perhaps a better way to think about it is that reality is a constant process of that probability turning into actuality. And we are, somehow, right in the middle of that process. We are not just in the universe. We are part of the way the universe becomes real. The world we experience is not the territory. It is the map, drawn by the interaction between the quantum wave and the observing mind. And the mystery of how that map gets drawn is the most fascinating question of all.